Okay, so I'm gonna make this quick video. Sorry for the quality. The lighting's not great, and the timing isn't great, but that's okay. All right, so the big idea, you watched the first video that talked about the consequences of the speed of light being constant and what effect that has on the time measured in a person's perspective reference frame. So one of the big things that we're going to talk about here is that time is relative. It is not an absolute concept. So that means that, for instance, imagine this is what sort of what Einstein did. Imagine that you're in a train and you're moving in this direction at some speed very fast. Okay, so it's got to be like very fast. You're not going to notice this at slow speeds. And slow speeds, I mean like up to 30% the speed of light. You probably won't even notice that much. We are going to envision a perfect mirror, and this perfect mirror reflects light 100%. That's important in this instance. Now, what we're going to imagine is that we have a light source, probably a laser beam, not an incandescent bulb like you see here. And this light source is going to emit a pulse that is going to travel upwards and come back down. Now, we're going to consider a reference frame moving with the train, meaning that the observer inside is stationary with respect to the event. Meaning, inside this, like imagine you being in a classroom or in your room, the Earth is rocketing through space at a constant speed, more or less. We are centripetally accelerating, we'll ignore that for now. But um, you don't notice anything. If you shine a laser beam straight up, it just comes back down, right? And that's the situation here as well. So what we're looking at is a view from inside the ship where you are going to trigger a laser beam, and from inside the ship, all you observe is it goes up. I can't draw it like coming back down the same path. I'll draw it beside it. And it comes straight back down. That's it. Now, what speed does it travel at? Well, Einstein showed that the speed, no matter what, is the speed of light. So it's always going to be c. And the distance it travels, in this case, it goes up by an amount d and then back down by an amount d. So the total distance it travels is 2d. Okay, and it travels at exactly the speed of light. Imagine you're in a classroom. Sitting in your room right now, you have a laser, you shoot it straight up, it comes back down. You don't notice anything. It went up, down, back. That's it. Okay. Well, we know this object's moving at a speed v, so we'll look at that in a second. But here, we're going to say, well, what is the speed equation? Well, the speed equation is the velocity, or the speed is distance over time. Okay? And this is our view from within the ship. All right, so we're okay. We're inside the ship. Bam, bam, comes back down really fast. So if I isolate for t, I could show that the stationary observer, and when I say stationary, air quotes, stationary meaning we're stationary with respect to the event that we're triggering. In this case, shooting a laser beam up, having it come back down. Now, I've isolated for t, which means I put t up here and speed comes down below. Well, how fast is the laser beam traveling? For all observers, it travels at c. So I have v down at the bottom, time up here. And what distance did it travel? I went up and down. Well, that's d plus d is 2d. Okay, that's equation 1. This is the time it takes for light to travel up and back, down in, I don't know what I wrote there, down in the reference frame of the ship. So, this is important. This is the time it takes for the light to travel up and back. That's the distance it travels, d plus d, divided by the speed of light. It's a very short period of time, depending on how big this distance is. That tells you what this observer is going to measure. Okay, good. So everything's fine. Now let's look outside the ship. And outside the ship, we're going to experience something perhaps different. So the reference frame that's viewed from the observer outside of the ship, we are going to call them sort of the moving observer. Um, so we're watching the motion, and again, I don't different textbooks and different way like different people do it differently in terms of like what they consider the stationary observer and the moving observer. But in this case, this is the one that I'm using. So here's the issue. Okay, we have a speed of the ship. There goes my ruler. Great. And that ship is traveling at close to C. Okay? Very close to the speed of light. In fact, it only has to be like 30, 40% is fine. And if you're outside of the ship, you are going to be standing here watching the ship fly by. And as this train, ship, whatever, is moving in this direction, you'll notice something else. You will notice that because the speed of light measured by you is also always c, it is going to travel at a diagonal, not a parabola, right? It's not being affected by gravity in this sense, and it's traveling super fast, and then it's going to come back down to a position here, like so, like that, okay? Now, it's traveling at exactly the speed of light. That is the most important thing to remember. So the observer here is OM, the moving observer, although we're not moving, but we're watching the motion happen. Now, if this thing is traveling at the speed of light, and it cannot travel faster, and this is where people, this is the thing that gets everybody. Everybody's like, no, 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 the ship's moving this way. And then you shoot a particle, a beam out. It's going to not only carry the speed of the ship, but the speed of the light. And therefore you add them together and this thing moves faster and travels a longer distance. Obviously, this is 2D, DD, but then this is like way longer. And you're like, no, no, no. It just means it's traveling faster over a longer distance at the exact same time. Absolutely wrong. Wrong, wrong. What you notice here is that since all observers measure the speed of light to be identical and exactly the speed of light, c, it means that this light beam here that's moving at the speed of light, even though it's moving in this direction, does not gain the speed of the ship plus that. Even though like we're like, no, no, but if you have a car and it's moving at 20 and then you 20 meters per second and then you throw a ball 20 meters per second forward, it's moving at 40 meters per second, the ball. Yeah, for really slow speeds. But we've already seen that relative speeds don't work this way. And you can do all the calculations with that equation I gave you before. And we find out that no, this light, it only travels at c. Which means that now you got a problem. Well, we don't have a problem. It's just the world is different. The universe is different. If this is moving at c, but is traveling a further distance, you have to measure a longer time for the event to happen. So this person goes short period of time. This person goes, and that is a longer period of time because the same speed, longer distance. That's time dilation. And this happens all the time. Doesn't matter if you're moving at 1 kilometer an hour or a trillion kilometers an hour. That will be the case. It's just that we don't notice it for really slow speeds. So we can do some mathematical analysis. And it's Pythagorean theorem at the most. It's not rocket science. It literally is not. So the distance up from here to here is d, the distance. Great. And then we can draw a little right angle triangle, tough stuff, right here. Okay, there we go. And we are going to analyze this a little bit more, and we say, well, okay, the distance from here up to here down to here, well, okay, I'm going to do something else. I'm going to say this. Well, the time it takes the ship to travel from here to here. So if we look at we know that distance is velocity times time. That's our basic equation. Then we say, well, okay, if I want to know how far the ship has traveled from here to here, like that, it's the speed of the ship multiplied by the observer's time, TM. This is the observer time. Observer's time watching the event. Okay, so they're watching the motion happen, which is why there's an M there. Okay. So what does that mean? Well, simply that means that the distance from here to that part there is just half that. If it's moving at a constant speed, we get that. Now you're panicking a little bit, I'm sure. You're like, okay, well, I've got the height D, this is a right angle triangle. I know that this part of the triangle right here is half of the total distance, which is measured as speed times the person that's watching the event's time. It's not the TS, it's their time that they measure. And so we notice as well that from here, that means that if the speed of the ship times the time divided by 2 is this distance, that means that the light beam from here to here is also the same time, delta Tm. But it's traveling at the speed of light, and so the light beam, this side is c delta Tm, and it's only half of it, because this is the totals from there to there, is divided by 2. Okay. So now we have a leg and a leg, 90-degree angle, hypotenuse, and we know Pythagorean theorem. And so we're like, okay, great. Let's apply Pythagorean theorem to this. And there we go. Now it's just basic math. We've done the hard work. We've kind of figured out the basic idea about what's happening. So we just apply a simple theorem that's figured out 5,000 years ago. Pythagorean theorem. And Pythagorean theorem's easy enough to understand. It says that if I take the hypotenuse, which was c delta Tm over 2, and I square it, it will equal to the one leg, which was half the time, half the distance, squared, plus the top squared. And you're looking at that, you're like, okay, not too bad. Well, I do know that if I square everything here, and I square the denominator, I'm going to get, so 2 squared is 4, right? So I can do some simple math here, and I can say just multiply everything by 4, because 2 squared is 4, 2 squared is 4. So if I multiply by 4, I can clear the denominator. So we're going to solve for delta Tm, clear denominator. Okay. So when we do that, we easily see that that becomes c delta Tm squared equals v delta Tm squared plus 4 delta d squared, like that. Multiply by 4, you can see that the, keep dropping the ruler, the 4 squared times 4 gets rid of it, 4 squared times 4 gets rid of it, but the 4, there's nothing here to get rid of it, so it stays as d squared. Now, just bring this over to the other side. I'm going to go fast just with my phone light battery because I have poor lighting in my room. My office is not very good, so we get that. I can just, I'm going to expand the bracket. Okay, c squared delta Tm squared. I'm not doing, this is like basic stuff at this point. So I'm not even going to talk about it. You can pause it if you want to. I'm going to common factor the delta Tm. Look at that. It's just sitting there. It's saying factor me, please. And what I'm left with is c squared minus v squared. Again, if you're not following that, pause it, take a look. I just factored out the delta Tm squared, and I'm left with c squared minus v squared. Okay, now I just go like this, do a simple division. I'm trying to solve for delta Tm. So I go delta Tm squared is 4d squared divided by c squared minus v squared, like that. And at that point, I'm now like, okay, fine. What do I do? Well, I'm getting delta Tm. So what's the opposite of squaring? Square root. And there we go. And now you're thinking, okay, what can I do with that? Well, keep going. What's the square root of 4? 2. What's the square root of d squared? D. Nothing's hard here. It's all easy. There we go. But here's where the fun happens. You're thinking like, well, the times are different. You've already told us the times are different. They have to be different. The light traveled further in the second scenario where you're watching it from outside, but it's still traveling at the speed of light. So therefore, there has to be a give and a take here. So what we say and what we do is we go, wait a second, from equation 1 on the previous page here, we said that delta Ts was 2d over c. Oh, interesting. Well, that means that 2d is delta Ts times c. Look at that. I now am connecting the what's called the proper time, which is the person watching or inside the event, to the dilated time, the person that is outside of the event. And look at this connection. We go delta Tm is c delta Ts divided by the square root of c squared minus v squared. The math here is grade 9, maybe grade 10 math at the most. Like grade 8 actually, you did Pythagorean theorem in grade 8. Okay, this formula here is not the way physicists like to show it, but it is correct. This is the formula. And so what is delta Tm? Well, this is now called something very special. It's called the dilated. Remember, dilated means to grow big, right? It's the dilated time. Your eyes dilate when it gets bright out. So that's your dilated time. It's measured with respect to the person watching the event. Okay? Delta Ts has another special name. Even though it's not correct, it's called the proper time. We call it the proper time because it's the one that we measure typically being the normal measurers of time, right? We're on the earth. We measure the proper time. People that are watching us move around are seeing a different time. They're measuring a dilated time to us. And so this is measured by the stationary observer inside the event. I call it like that. It gets complicated, but inside the event. And different textbooks use different notations. Sometimes you use prime, or they use 0, like for not. But anyways, this is what I like to choose. Okay. So the proper time is always going to be smaller than the dilated. The word dilated literally means bigger. So this side is going to be bigger because whatever you do, whenever you take c squared minus v squared, the denominator is getting smaller, which means that if you're taking a smaller number and you're dividing by anything, and you take the delta Ts, and this number here is going to be less than yeah, I'll show you in a second. So we're going to simplify this. Simplify. Okay, by simplify, I mean sort of make things more complicated, but this is the regular formula. So to simplify, to get the formula that everyone uses, is we are going to leave the top, C delta Ts, and we do something fancy. Okay, and the fancy thing I'm going to do is this. I am going to factor out c squared. We did this the other day, actually. If I pull c squared out of here, I'm left with 1, right? And if I pull a c squared out of here, I'm left with v squared over c squared. Look at that. C squared times 1 is c squared. C squared times negative v squared over c squared. The c squareds cancel. You're left with negative v squared. Pause that, rewind that. Again, this is grade 9, maybe grade 10 factoring at the most. Now, we go here, we go c delta ts. Oh, square root, these are multiplied. The square root of c squared is c. And I can't do anything with the next part. And look at that. The c popped out, because if I want to move it back in, I have to square it, so it would be c squared minus v squared. It's exactly this formula right here. Bam, bam, they divide out. And so the final time dilation formula becomes delta Tm equals delta Ts divided by 1 minus v squared over c squared. And that's it, right there. This is the dilated time. This is the proper time. And this little thing down here is going to get a special name. And you'll see that a little bit later. Now, there's some things to really understand here. Is that v squared divided by c squared, right, is always going to be a really tiny number. And so 1 minus anything is a number that's less than 1. Doesn't matter how small this is, right? It does not matter whatsoever. Now, v could be the speed of light. The object could be traveling at the speed of light, in which case you get 1 minus 1, which makes no sense because you have 0. You get infinite time dilation, meaning no matter how much time passed in the observer in the ship, an infinite amount of time would pass for everybody watching it. And that'd be like the end of the universe. We'll talk more about that later. But since this bottom denominator, no matter what, you're taking 1, subtract any number, is always less than 1, even if you square root it. That means that any time, that means the denominator is always less than 1. And if you take any number and divide it by a number less than 1, this number will always be bigger. So no matter what, the denominator is always less than 1. And so delta Tm is always greater than or equal to delta Ts. Always. The dilated time will always be greater than, and the only time it can be equal to is if v and c, if the speed of the object is exactly the speed of light, in which case you'll get, it doesn't make sense, but anyways, your delta Tm is going to be greater than or equal to delta Ts. Okay? And that's because the denominator is always less than or equal to 1. That learning right there is the most important part of this. We use Pythagorean theorem to get here. The speed of light is constant. This delta Tm, the dilated time, must always be greater than the proper time, because we can't go to the speed of light. Obviously, we'll divide by 0. And that so that means that no matter what, an object in motion, if you are in a ship measuring time, people watching you will always measure more time go by. So if you're in a ship going really, really fast, and you can put in some numbers for speed, and you say, oh yeah, okay, so it took me 10 minutes to exercise, but I'm going really close to the speed of light. So you're taking 10 minutes divided by some massive amount of time, or sorry, some really small number, and somebody out here might be like, I just saw an hour go by. So they watched you work out for an hour in a really slow, laborious method, but you only measured 10 minutes in your time. And it sounds like ridiculous, but if you allow the speed of light, or we pin the speed of light to be constant for all observers no matter what, unchanging, then that is a fact, and that will happen. And so that goes back to this point here, where this is where the big misconception happens. People are like, no, this is it. It traveled further but traveled at the speed of light. People are always, the problem comes when you say, well, the speed of the ship plus the speed of light means that the light was traveling faster because it had the speed of the ship plus the speed of light to go to here. And therefore it traveled faster, longer distance, exact same time. Wrong. It could only travel at the speed of light. All observers measure at the speed of light. So if it traveled further at the same speed as it did to go up and down for the other observer, it had to take longer. Done. All right, in the next little video, you're going to learn how to use this, how to put calculations in, fast ways to do it in order to see what those things look like. And also, we're going to learn that we never notice this because we have to go really, really fast, like 30, 40% the speed of light, which is unbelievably fast. We haven't even got there with regular objects outside of like particles. And so we don't notice it. But with satellites, we can actually measure it to like the 8th decimal place, and it does work. Okay, so that's the main lesson. And you can go on to the next one after this, which shows you how to do the calculations.